Okay, hello and welcome everyone to the afternoon keynote session. Thank you for coming. It's a real pleasure to introduce my colleague, longtime collaborator and friend, Hyesoon Kim, who's an associate professor in the School of Computer Science at Georgia Tech. She comes from the computer architecture community, has been doing a lot of pioneering work at the intersection of computer architectures and compilers, particularly for heterogeneous systems. So this includes GPUs, but also is expanded to include FPGAs, as well as processing and memory systems. And in fact, she has a Best Paper Award from PACT, which is one of the architecture compiler conferences in 2015 for some of her work on processing in memory. She is very active in the computer architecture community, widely recognized. In fact, she's a member of the Micro Hall of Fame. So Micro is one of the top 2 conferences in computer architectures, and the Hall of Fame, you get inducted, I guess, when you publish 1 million papers in that conference, which she has done. So anyway, so it's a great pleasure to have her come and visit our community and tell us what she thinks about performance modeling and sort of the future of heterogeneous architectures at all scales, from embedded to supercomputer systems. So please join me in welcoming Hyesoon Kim.
Okay, thank you, Rich. It's my great pleasure to give a talk here. As Rich mentioned, I'm mainly coming from computer architecture community, but I'm going to talk about how this computer architecture research can be also used for more application developers. So I guess as coming from the hardware person, I will need to show the Moore's law chart just for shortly to show what's my background. So as you can see from here that the number of these transistors are increasing significantly, but we are in the stage a little bit of saturated. So as of the outcome, what happens is we are going into the more special accelerator errors. So there are lots of special hardwares right now. So we all aware of these GPUs, and there is AGX and PIM, or processing near memories, and APUs that combining GPU and CPUs, now FPGAs, and also soon we'll start to probably see the quantum processor as a part of this special hardware. So as architectures, it's great to produce this kind of different architecture. That means we can continuously produce different architecture and optimize it for it. But what does it mean, this to this software or programmers? So that gives a job to these softwares and then asks them to decide where we should execute this code. How do you decide we run a withdraw die and decide where we execute? Of course not. Then what do we do? So modeling has been used for this helping for application developers in mainly 2 directions. The one is decision of converting code for new architecture. So when you have a new architecture coming, then we are wondering whether this new architecture will give any benefit. And also when we convert the code, we're also wondering about whether we get the best performance from the architecture or not. So modeling helps to provide these kind of trade-offs. The modeling also gives some benefit to the hardware designers. So modeling mostly used for the fast simulations or architecture designers to explore different design spaces. And also sometimes architecture designers also use this modeling for decide the resource management, such as if you have caches, then how do you split these caches for the CPU versus GPUs, or have memories, and how do you split different architectures. Also the compilers also use this modeling for this resource management, that sometimes we can decide all decisions at static time. That's what the compiler can do. Or the compilers can also decide what kind of optimization you want to do, and based on this kind of modelings. And today, I'm going to mostly focus on our group's effort about helping the decision of converting code for new architectures. So we have a different architecture, so we have a couple of case studies that I'd like to share with you. So first case study is CPU versus GPU. So motivating problem was, if we have a CPU code, should you convert the code for the GPU or not? And can you know that even before we convert the code, because converting code might take 100 hours or thousands of hours. By now, most of the code is converted to GPU, but still questionable that do we want to spend 1,000 hours to converting code and get 2x benefit, or we get more performance benefit. And so if we wanted to know that result, even before converting the code, then that would be the best to estimate how we share the resources. So in order to know that, the first things to consider was considering the computer power differences. So if we had GPU code, just like this is a snapshot of this GPU kernel code, then we could have executed some of the execution time. There have been several analytical models to estimate these execution times. One of the execution model was using a top-down approaches that we have execution time, and execution times can be broken into the three main components, compute times, memory times, overlapping times. And in these compute times and memory times, that how this compute and memory can be overlapped, that will change the performance significantly. It's because in architecture, the compute time has to be serialized because we have a finite resources, but memory can be easily overlapped if we can take advantage of these memory level parallelisms. And then if we can overlap between this compute time and memory time, then we can reduce execution time significantly. So the main performance benefit that was coming from this, how much we can overlap this compute time and memory time by using a thread level or memory level parallelisms. On top of that, in execution time, if we consider what is a serial or what is in parallel, we can also consider, expect these execution time differences. And in the parallel part, we can also consider what are the instruction throughput. So main compute execution time on the GPU is heavily depending on these thread level parallelisms. But not only that, we also need to consider instruction level parallelisms in the GPUs as well. So effective instruction throughput is what we need to consider, especially in these high parallel architectures. That we have to consider warp sizes and SIMD widths and pipeline stages. And then ITLP, the combined instruction thread level parallelisms, are the ones that consider both of them. And then for the serial execution time is mainly coming from this execution resource conflict, that there is a synchronization overhead, special function units, and some of the branch divergence, and then bank conflict. Those kind of these resource conflicts are giving a serialized execution overhead. And if I talk a little bit more about IELP, it's an inter-thread IELPs. If we have only one instructions, then even if we have some IELPs, there is a stall time. So if we have a many number of threads, then we can start hide these instruction level parallelisms, then can hide these latencies. So combining both instruction level and thread level parallelisms, we can estimate execution times. But the problem is, going back to the original problem, the problem is we only have this CPU code. Then how do you predict the GPU execution time? Because we don't have a GPU code. Yes, so we cannot analyze this kind of, we cannot use this kind of analyzer model. So what we did was we considered the machine scale factors. So most important part of the performance for this CPU and GPU is considering the peak GPU performance and considering peak CPU performance. And then also in the CPU case, or actually in both CPU and GPU case, SIMD instruction that changes a lot of these peak flops. So how much this code can be parallelized, how much the code can be synchronized, vectorized, that is one of the key factor of deciding performance. So by just considering this scaling factor of the machines and then code these vectorizations, we can estimate the performance of this GPU code by just only looking at the CPU code. So the chart that shows in the right tab shows the performance estimations versus using a CPU performance to GPU performance. Surprisingly, most of the time we get the pretty good result, and there is some outliers. That outliers I will talk about this. So this one was using a very simple live comparisons, but we can still get regional performance. And there have been other approaches trying to get the performance of the GPU from the CPU code, mainly based on the machine learning techniques. So that if you have enough data, then we could also estimate the CPU to GPU performance. But these are only considering these compute performance differences. Probably, perhaps, the other most important part, and that's why there is some discrepancies in using this simple naive mechanism, is considering this data movement cost. So most of these heterogeneous architectures are based on accelerator-based model, which means there is a host processor and there is accelerators. In this case, this is a CPU plus GPUs, but this model can be also considered as other kinds of accelerators. When you have a CPU plus GPUs, and CPU is the main one that launches a job, and CPU is the main one who collects the data and who reads data from the I/O devices. And then data has to be sent to GPUs. So then when even though we might improve performance on GPUs, if we spend majority time on sending a data from CPU to GPU, then we'll not get any performance benefit. So first of all, what we did was consider the performance time, the differences between the compute time on CPUs and compute time on GPUs, and then consider transfer time of GPU. In this CPU plus GPU model, we use PCI Express bus so that by just estimating working set sizes, we can estimate transfer time fairly easily by considering the bandwidth of PCI Express bus. And then we can consider whether the GPU time is significantly greater than CPU time or vice versa. And then if that difference is relatively small, then we can start worrying about the caching effect. Because so far we haven't talked about anything about caches, and we only mainly think about compute power. So then let's worry about the caches. In order to worry about caches, the most important part is estimating working set estimations. The working set size predictions have various ways of doing it. One is reuse-based analysis. They compute how many memory accesses, how many unique memory accesses are there in between two reuse that give some of the working set effect. There is a long history about using a reuse-based analysis to estimate working set sizes, but often the cost was very high to estimate that. The other approaches are heuristic-based approaches. And the third approach is using a profiling-based approach. The profiling-based approach will be maybe the most accurate if we have this good sampling data. Often we have the problem of getting a representative sampling data because the runtime behavior might change significantly, which we'll talk about later in this talk as well, that depending on the input, this can vary significantly. But some of the workload, that behavior is quite predictable if we have a good sampling data. So that one of the techniques that we have proposed was the chip profilers that just by only profiling the cache, one set of the caches that have a different workings at different set associativities, we can estimate the required cache sizes. Then also give some estimation of the cache hit rate in different cache sizes. So in this method, that what we do is just doing one-time profiling and get different cache rate for the different cache sizes. That's the cache. But then there's another important part that we have to consider if we offload. One of the other part is not only whether the working set size is, the other issue is data sharing between two different units. So this example shows different offloading scenarios. Let's assume that we have 4 different regions, region A, B, C, D, and we have choices of offloading some of the regions into the GPUs. The two scenarios we're talking about is region A and C are offloaded to GPU, or region B and C are offloaded to the GPUs. The issue of this is depending on what regions are offloaded to GPUs, the performance on this CPU, the cache behavior of CPU or cache behavior of GPU can vary. The main whether we have to send the data to this other unit, that's one problem. And the other problem is what will be the remaining data sizes. So for example, in this example, the data comes from the A, and then if the data from the region A data is used by the region D, and if in the first scenarios region A's are executed in GPUs, then region D, if they share the data from region A to D, then the data needs to come from GPU to CPU. In scenario B, both region A and region D are running on the CPU, so in that case, the data from region A are remaining on CPUs, and then region D can simply use it. And this also gives also another problem, it shows another problem. If A, B, C, D were all running on the CPUs, then even if A and D were sharing the data data A might have been evicted by region B and C. In case of scenario B, because B and C are offloaded to the GPUs, the data from region A still remain on CPU so that we can use it. So we can construct these kind of different scenarios. And depending on these different scenarios, the cache behavior changes. So in order to estimate performance behavior with the cache behavior, then what we need to do is we need to construct different kind of offloading scenarios. And then we have to estimate whether the data will still remain on caches or not, depending on different offloading scenarios. So the approaches that we took for solving this problem was we emulate different offloading scenarios. Then we can reduce a lot of cases by just simply assuming that whether data will be evicted by next regions by predicting the working sizes. And then if the data can still remain these caches, then we can construct different workload emulating scenarios and estimate. So that using those methods, we were able to predict the performance from this CPU called the GPUs, and then identify the best offloading scenarios. So that was the one example how we use performance models to predict its GPU performance, or when you run on CPU plus GPUs. The compute power could be predicted by fairly simple analytical models, but we were limited by memory behaviors, and it requires somehow the emulation method to predict the performance benefit. The second method we have used, second case studies we have done was CPU versus the PIM. So the PIM, process in memory, or some people might call near data memory. There are various terms are used for the PIM. The basic idea of the execution model of the PIM is we are shipping the computations where in the data is. But there are various spectrum of what PIM means. Some people might think that we're just offloading a couple of instructions, or it can go all the way down that there is a very tiny, or there are some processes very near to the memory, and then so that it can offload full computation into the PIM. So we look at both of these cases, and then we're trying to provide, again, trying to provide the guidelines that what or when is good to use this PIM. So first, I provide a little bit of background about the PIM. Our PIM model was based on HMC model that was introduced to Micron. So this was based on the 3D stack memory, and the bottom of the 3D stack memory, there's logic layers. It can compute simple computations. And then in the HMC 1.0, it was able to only use a 3D stack memory, but the spec of HMC 2.0, then it was able to perform a few operations, such as arithmetics and bitwise or Boolean and comparisons. Then the question is, what can we upload to the PIM, and when can you get benefit? And then in order to use these approaches, in order to use the PIM, then what we need to do is the left side shows the CPU, and the right side shows this 3D stack memory with the PIM operations. Then we have to send command line with this instruction that what we want to produce, what we want to compute, and then we need to send address. And then once the computation is done, this HMC send back to acknowledgement. That way, the PIM processor can know what computation done and can move on. So when you offload these computations, the key part, the key consider factor to think about is cache miss behavior. If we think it's high-level pictures, if we bring a data and then reuse over and over in the processor, because that means we get the benefit of using a caches. But if we bring a data from the memory, but we just use once and then we throw away, then we don't get the benefit of the caches. So obviously, if we use the cache benefits, then it's better to use the caches. If there is no cache miss behavior, then it's probably better to just compute on the memory and then and do not bring the data from this memory to the core. So we consider all this benefit with the we characterize it based on cache ratios. So this chart shows that x-axis shows the cache ratio, and the y-axis shows the bandwidth saving effect. So if you have a high cache ratio, the bandwidth saving effect is very little. But if you have a very low cache ratio, the bandwidth saving effect is very high. As you remember, this previous slide shows, we always have to send the command line to compute some operations. So we still need to send the data to this processor, not the data, the command computations. So we still need to send some computations, but then what we are, and also we need to get acknowledgement that also consumes the bandwidth. So we need to consider those small bit differences. So this equation shows the difference between this, how much bandwidth we're saving by offloading into the PIM. So this shows the bandwidth saving benefit, but the problem of the performance in the CPU architecture or GPU architecture is not all applications are limited by memory bandwidth. If we are not limited by memory bandwidth, the bandwidth saving effect should not give any much benefit. So that shows the performance benefit that presented with the bandwidth saving benefits. If the applications are not limited to bandwidth savings, then you don't get any benefit by using these PIM offloadings. But if your applications are bandwidth sensitive regions, then we get the benefit. That was the first our understanding about the PIM. That we see that in the CPU cases, it was limited by bandwidth, and GPU cases, it was heavily limited by bandwidth. So we can see some benchmark, we get the significant performance benefit. But many of the CPU benchmark, we didn't get that much benefit by offloading to the HMC. But then we also found another very important factor that PIM could benefit. That this is also showing this ratio based on the cache miss ratios. So another important factor we found in this PIM was the benefit of atomic operations. So that comes with the memory conscious models. So what it means is, in the CPU or GPU, especially in CPU architectures, when there is multiple threads are accessing the same data locations, then in order to protect from these multiple threads are accessing data simultaneously, it uses atomic operations. But when the CPU uses atomic operations, then because the CPU was increasing MLP, or even the GPU were trying to increase MLP, they generate memory requests all in parallel. But when it sees these atomic operations, it starts drain the pipeline, and it starts to execute all these atomic operations in serial. So there is a huge performance overhead of just operating atomic operations in CPU. But if you offload these atomic operations on this PIM, we do not need to worry about this parallel memory access effect because operations done in the memory itself, only one place are changing the data. So that means we do not need to worry about these multiple multiple compute units are changing these locations. So that naturally gives parallelism effect. So when original operations were done in atomic operations, and if we offload that into this PIM, then we can remove this additional overhead that was the CPUs having it. That provide additional benefit. So what we found was, if we do not worry about atomics, then the performance benefit we can get from the PIM was only when the cache miss ratio was really high. But if the operations was done on the atomic part, then what we found is, even if the cache miss ratio is relatively low, it still gives a benefit by offloading the PIM. That's because we can eliminate this atomic operation overhead. So that was another important benefit we found throughout these PIM operations. And so the PIM was just offloading one single instructions. But the PIM operation the PIM programming models have a various spectrums. We can offload just a single instruction, or we can offload entire kernels. Entire kernel means we are assuming that the processing memory has an entire core that's sitting just next to this memory. So when we offload this entire kernel into the PIM, the bandwidth, although the PIM itself gets a great memory bandwidth, but bandwidth saving effect is not the crucial to decide what needs to be offloaded to the PIM or the CPU. What we found was performance difference was the main factor that decide what goes to the PIM versus what should go in the CPU. Because now if we offload entire kernel into the PIM, that means the PIM also has a full compute capabilities. Sometimes we get benefit by offloading PIM because now we save some bandwidth, and then memory access latency is relatively short, because it's close to the memory. And then because it's close to memory, we often use a very shallow cache hierarchies, so that anyway we offload the kernel into the memory, which do not usually have that much cache benefit, so we do not want to have a high cache or large caches and a deep cache hierarchies. So the cache is just additional overhead now that we reduce those overhead. And then also we can reduce cache current traffics because the operations are done uniquely for the memory regions. But sometimes we lose performance on the PIM because PIM cores cannot be really high performance as CPU, mainly because of thermal constraints. So the PIM cores are relatively low performance cores. And the PIM cores need to have a smaller cache sizes because the PIM cores are limited by memory chip sizes, so we cannot really put too big caches. And then there is some NUMA effect. That means if the computation is performed in the same location as where data is, that's great. But if we need to get data from another DIMM or another HMC chip, another memory locations, and now suddenly the latency becomes really high. So it's very critical to carefully design this memory layout that compute and data needs to be located together. That's a fundamental, that's a traditional problem, but that problem gets much more severe in this PIM context. But in this case, when you offload these kernels, these performance differences were relatively give a good indications one needs to offload to the PIM or not. But then one of the reasons that we want to use the PIM was energy savings. Because the main idea is if you do not send the data from memory to the core, and if you just perform the computations on the memory, then we could save the energies of the data transfer. So to understand the behavior, also model the energy behaviors. So in this case, the model was that each of the HMC cores had a full capable of computing cores are there. Then there is a host processors are there, and then there each of these stacked memory has a PIM cores. And then we consider energies models. So total energy consumption is the sum of the host energies and energy that consumed by the PIM and data transfer energies. Then host energy can be broken down to the core energy and on-core energy, which means like caches and other components. And then core compute energy is mainly whether this is active or this is idle, because both of these host and then when you offload to the host and versus the PIM, then often also need to consider the idle time, because if you offload some computation to the core, then host can be idle. And then on-core part is mainly about this number of channels times the total time. And then this one is energy, so often computer architectures mix up between power and energy, but this really means the energy, so everything needs to consider the time effect. And then cache energies needs to have a static cache energy and dynamic cache energies, and static means it needs to consider the liquid power, and dynamic energy is proportional to the excess of these caches. And then transfer energies, okay, sorry. Yes, and the transfer energy is the PCB transfer between this host core and the PIM cores. And then we have the similar mechanisms for the PIM and host, and both have the similar energy breakdowns. The main difference between PIM core and host core is usually the compute core sizes, because PIM core tended to have a smaller core sizes and shallow memories and shallow cache, and then host core has more bigger caches and then more high compute powers. So then when we model it, there is a part that we can model from this architecture design parameters, and then there is a part that we estimate based on the applications. So the yellow component highlights that we can get this data from the simulations, and the orange part highlights that we estimate is based on architecture designs. So that similar effects are done in the PIM, and in case the PIM also needs to consider this data transfer cost of the energies from this host to the PIM, and often that consider the SerDes energies. And found that the SerDes energies from this PIM to from host to the PIM also consume significant amount of power. That is another important factors that we learned from this energy model was the SerDes power. Anything that needs to send it from the host core to the PIM core needs to be serialized, and that energy consumption is very significant. So that we model this, and then again, yellow part we estimate from the simulations, and the orange part based on the circuit and architecture models. So in that case, if you consider energy, that in trading trade-off is the MPKI, the cache misses per thousand instruction matters the most, because we consider the energy, the energy delay product. Then no MPK benchmark increase EDP significantly. So even if you only consider the performance to decide a PIM, then compute core, considering the compute core performance was good enough. But if you consider the energy, then the trade-offs start to change it in the middle MPKI, and that makes a decision that whether we want to use the PIM versus the host computations. Another part that was important in the PIM was thermal effect, because the PIM cores that we put the compute under the 3D stack memory. So if we put too much computation under the PIM, that they might exceed the temperature, then that might hurt the performance. So to understand that, we also model the temperature effect. The first, we start from measuring the existing HMC. And by modeling by measuring the temperature, we model temperature behavior. So this is a test board from Micron that has a HMC chip and then testing FPGA. Unfortunately, we have to measure the temperature that on top of this heatsink, but then we model the heatsink so that we can estimate the thermal effect. So if we use high-end active, means we were intentionally provide more cooling effect, or we don't provide enough cooling effect, then you can see the temperature differences. And what happens in this case, if we do not provide enough cooling effect, then this HMC will shut down because it just exceeds the temperature. And that's also not only shutdowns, though what happens is in these DRAMs, as you increase the temperature, there's the power consumptions are different, and then there's a operating temperature range that can sustain this hardware. So in the case of HMC, the operating temperature was 0 to 105. So if we upload more and more computations into this HMC, then we start increase the temperatures. So depending on whether we use a very passive, just only have this heatsink, or we have a really powerful this cooling air, the temperature increases are varied. If you use really high end and server end, then even if you upload 300 gigabytes per second, it doesn't exceed the temperature. But if we use like low end cooling systems or just use only passive, then it reaches the 105, then we shut down so that we cannot offload anymore. So we model this this relationship with the PIM versus peak temperatures. So then we understand that we have to operate these PIM operations under the temperature boundaries in order to get the best performance. Because also if we increase the DRAM temperature, not only that exceed the temperature limit, it start to slow down the DRAM frequency. So then they will actually also degrade the performance. So based on these models, what we understood was if you have to control the pin offloading rate based on the temperature monitors. If the temperature is low, then we can increase more compute into the pin. But once it reaches a certain temperatures, then we have to make the trade-off, and then we might need to cut down these offloadings to maintain the desired temperatures. So that the conclusion in this model was PIM intensity needs to be controlled. So let's talk a little bit about newer architecture. One of these newer architecture is unified memories on CPU plus in GPUs. So the newer GPU architectures, they provide unified virtual memories that with the demanding pages. What it means is the GPU can use entire memory systems on the CPUs. Now, that gives a lot of flexibilities to programmers. The programmers do not need to worry about what fits in the memory, and then they can use entire CPU memory as if this is a GPU memory. So that, in the idea-wise, it is great. But downside of this approach is the management that what goes into GPU and what goes into CPU was managed by the drivers under the hardware. So what we have observed for this case is exactly same graph benchmark. This was the BFS. And then we changed the working set sizes by changing the data sizes and measure the performance. They're running on unified virtual memories. The y-axis shows taps. And the x-axis shows different data structure for the same BFS. If the graph fits in this GPU, so this is just the same benchmark, but having a different graph sizes. If the graph fits on the GPU, we get higher git taps, that's more than 2. But once it exceeds this the graph size exceeds the GPU memory sizes, then performance drops significantly. It doesn't even reach the PCI bandwidth. It's mainly limited by this bandwidth coming from CPU to GPU. So this kind of gives important factors that even if we were able to model performance model for the CPU and GPU, and even if we can predict some of the memory behavior, if the memory behavior changes significantly, even if the same code, that can change the performance significantly, especially for this kind of unified virtual memory architectures, that this is the graph size is the most important factor to decide the performance. And let me talk about a little bit more on newer architecture, which is FPGA. So FPGA is getting a lot of attention these days, and then people are trying to offload a lot of computations on FPGA. One of the questions we like to answer is when is it good to use FPGA? FPGA versus ASIC chips, FPGA versus GPU chips, or versus the CPU chips. We've been trying to get the same mechanism to predict the performance of FPGA from the CPU code or GPU code. Unfortunately, we weren't able to do it yet. And then one of the challenges of modern FPGA performance was FPGA design space degree is very wide. And then for a given FPGA, we have a fixed number multipliers DSP unit, and then most of the rest of the units are programmer logic. So virtually any design options are possible if we fit into this FPGA. So performance precision accuracy is not good enough in our current technologies. So this is one of the important future research topics that we'd like to explore, how do we predict the performance from the CPU code to the FPGA, that's so that we can guide what can go to the FPGA. One of the things we were trying to do to reach that goal is actually offloading some of the computation FPGA and trying to understand performance benefits. So one of the things that we've been doing is we were looking at the latest workload that is popular in autonomous driving agent. These are just toy robots that we're building in our research groups, and all these workloads are there. And then one interesting part of this latest applications, and if you go down, then it goes down into these math equations that I feel like I have to show some math equations that they know to present in the PPAP, so, the SIAM. So I show these equations. So that's one of the applications we'll be looking at is a SLAM, and there are two popular algorithms, and then we were trying to offload these SLAM algorithms in FPGA and see whether we can get enough performance benefits or not. So we implemented the SLAM onto the FPGA. But one thing that we wanted to also see the same trend we see in FPGA is data movement. Because even if you offload some computation FPGA, it still needs a CPUs and still needs memories. And it could be a CPU. The reason it needs a CPU is because it interacts with the sensors. So if you get rid of the CPUs and if everything runs on FPGA, then it's a little bit different story. But because it needs to interact with the sensors, then eventually most of the part, the performance is dominated by this data movement cost. So in this case, we were able to achieve the significant performance benefit. The red bar is performance benefit we got, and lower is better compared to other techniques. Then one of the reasons we were able to achieve a significant performance benefit was we were able to offload more computations and reduce amount of data needs to be transferred from the CPU to FPGA. So the conclusion is hardware has become more and more complex. That's a good news for computer architecture, but probably not a good news for these application developers. But still, we have the same philosophy that has been in here for a long time, that it's understanding compute boundaries versus memory bound is still the most important criteria. The difference is the compute boundaries change it depending on the architecture design, depending on different accelerators. This what becomes compute bound, or even if it was compute bound, might become memory bound. These are changing. That's something that you have to understand. And then modern newer architecture is the ongoing task, such as FPGA, and then probably if the quantum becomes popular, then modeling there will be also another interesting problem. And then estimating data movement cost is probably still the biggest challenge. Where do you get data? You might get data from the CPU because it's connected to I/O devices. You might get data from the sensors. That's the more and more newer workload is getting a lot of sensors and using lots of sensor. One of the robots that we're building, we start with only one Raspberry Pi, but at the beginning we had only one sensors, but end of the project we have like 7 different sensors. So in the newer workload, there are lots of sensors, then sensor data needs to move through it, and then we improve compute, but we couldn't improve too much about this data movement. And also, not only performance, also need to consider power and thermal. That needs to be modeled and needs to be considered. Okay, now this is the end of the talk, and we have to take any more questions. Thank you.
So we have time for maybe 1 or 2 quick questions.
Yeah, there's a new commercial player on the scene, UpMem, that's doing computation in the DIMMs. I was wondering if you had a look at them at all.
Sorry, I didn't hear the question, sorry.
Oh, have you had a chance to look at UpMem, for example?
UpMem?
Doing computation in the DIMMs themselves.
Yes. Yeah, so we're also looking at that. That's the part of these PIM models that offloading this computation in the PIM. And our model was targeting for more about 3D stack memory, but that can be also applied to these 2D memories. So yes, this PIM model can be applied to these DIMM computations. Then most of the time, that's only the parameters, because most of our models that we show as more abstract numbers, and these abstract numbers are changed based on technologies. So if you use the DIM method, then the amount of computation is less, and then, but we have high bandwidth, but then we need to also limit it by the bandwidth and the latency between different DIMMs. So the NUMA effect will be much higher in the DIMM operations.
Thanks for the talk. And I'm curious about how to handle the long latency while accessing the DRAM directly without cache about the PIM. Or in another word, how to handle the data hazard if the DRAM access latency in the pipeline.
So we cannot really reduce the DIMM latency. So what we could do is we move the computation close to the DRAM. So that will reduce the DRAM latencies.
Okay.
Yeah, so the compute on DIMM is one of the examples for that.
Oh, how is the improvement of that? Maybe to how many cycles about the latency it can improve the two?
Well, so that, for example, the typical DRAM latency might be like 400 cycles, and if you offload that, then basically we reduce lots of tail latencies. Yeah. So if the DRAM itself latency might be only 80 cycles, but because we eliminate the tail latencies, so if typical latency on CPU might have 400 cycles, that's because of this long latency operation. So if you offload that into the PIM, then the latency might be reduced like 40 cycles or 80 cycles.
I see. Thank you.
Any last quick question? I'll ask one quick one. You didn't talk much about programming for these new classes of devices. I don't know if you have any thoughts you wanted to share about prospects for each of them, how to program them.
That's good questions. The one thing I could just say is the newer architectures, still we feel like we are going back to matrix multiplications. I think a newer emerging workloads requires more and more those understanding of the matrix operations. So that's what I feel about these newer generations.
Well, with that, we'll close the session. Thank you for your attention.
Thank you.